next talk will be by Jean-Michel Fried, and it will be called Passive and Active Radar Using Software-Defined Radio. So please welcome Jean-Michel Fried.
Thanks for the introduction. So I'm Jean-Michel Fried. I'm associate professor at University of Franche-Comté in Besançon, and I'm working at the time and frequency department of a French institute, FMCW, which is irrelevant to this presentation unless I tell you why I'm working on developing short-range radar systems. When I started working on stable oscillators, I asked my colleagues, why are we funded to develop high-stability oscillators? The classical answer is we're doing this for global navigation satellite systems, GPS, Galileo. We're doing this for radio astronomy, and we're doing this for radar. And the first two answers were quite obvious. Okay, I understand why we need high-stability oscillators for time transfer over satellite links and for VLBI. And I never got a clear answer why radar systems needed a high-stability oscillator. So I started building mine. And what I want to share with you is 10 years of exploration of short-range radar system development in a quest to understand why they need high-stability oscillators. And don't ask me why, because after 10 years, I still don't know. So let me define a few words of this title. So first of all, what is radio frequency detection and ranging? So an electromagnetic wave propagates at 3.228 meters per second, which doesn't tell me anything. But if you divide numerator and denominator by 10 to the 6, the speed of light is 300 meters per microsecond. It means that whenever a light wave starts from here, goes 350 meters away, bounces on the target, and comes back, we spend 1 microsecond. And 1 microsecond, by today's standard, is very easy to measure. So electromagnetic waves are propagating, whether generated on purpose or surrounding smog, and they are reflected either by metallic or dielectric interfaces, and they come back to us. We wish to measure maybe time of flight. We want to measure the direction of arrival. So we have two big types of radar that I will be exposing in this presentation. Monostatic radar, where the emitter and the receiver are collocated, and multistatic, bistatic radar, where the emitter and receiver are not located. So initially, the first patent about radar, which was just about detection, was what we would call today for scatter radar, is an emitter whose beam is intercepted by a target. Now, by measuring the time of flight, if you have a bit more advanced electronics, you can range the information. And furthermore, you know that if this target is moving, you will get a Doppler shift. Because the Doppler is on the incoming and outgoing wave, it's 2 times the carrier frequency times the velocity divided by c. Sorry, this is upside down. So we have this kind of information that we gather from electromagnetic signals, and what I want to show you is how software-defined radio allows everyone today to build their own radar systems. A last word, what we have as non-intentional target reflections, some people will call it clutter, unwanted reflections. Some people will call these their targets. Now, because most of you are not allowed to broadcast electromagnetic signals, I will conclude this presentation with passive radar, where you're just using surrounding electromagnetic signal for ranging and time of flight. Now, most of the time, you know World War II for atomic bomb development, Manhattan Project. I just cite here a few of the general public literature showing that the radar had a strong impact on the Second World War as well. And actually, talking of Second World War, it's really nice to see that the word radar was a unification of radio detection, radio direction finding, RDF. So in 1940, there was an American Navy admiral who decided all this electromagnetic stuff should be called radar. So this is the creation of this word and its common use. So that's much for radar. Now, software-defined radio. If you're not familiar with software-defined radio, the objective of SDR is to try to minimize as much as possible the analog radio frequency front end and move all the processing to software. And that's so much fun because it mixes my two interests, physics and radio frequency engineering, and computer science, high-performance computer science. And so the ideal software-defined radio would be to connect the antenna, maybe amplify a little bit the signal to an A to D, analog to digital converter, and this stream of data would be software process. Now, this is challenging for multiple reasons. You need to sample faster than twice the carrier frequency. You might have strong interference sources within the band. So this is not really desirable. Current software-defined radio are actually using zero intermediate frequency, which means you take the radio frequency wave and you mix it with a carrier frequency, the local oscillator, tuned to the center frequency of the signal you're interested in, and the output of the mixer is actually the one which is sampled at sampling frequency Fs. Fs selected so that enough of your bandwidth is within the spectrum that you collected. So remember, every time you sample at Fs, your signal is ranging in the spectral domain is going from minus half the sampling frequency to half the sampling frequency. That's Nyquist theorem or Shannon sampling theorem. Now, if you were to just take this spectrum in a radio frequency band and bring it to what we call basebands around 0 hertz, this spectrum being a real quantity would have to be an even function. And obviously, there is no reason for this spectrum to be even around the current frequency. So if you have a non-even shape of a spectrum, naturally, you must describe these quantities as complex numbers, meaning you must have two mixers, an identity and quadrature. I will not get into the details, but just to justify that throughout this presentation, I will be manipulating complex quantities, complex in the sense I plus jq, j squared equal minus 1. So that's the outline. How can we mix these two knowledge of SDR and radar systems? Now, most of you might know radar systems from military applications, but actually radars are everywhere around you. I collected a few information on the internet. These are not mine. Of course, you all know air and marine transport control, but radar are commonly used for bridge or building deformation and vibration detection. There is one Italian company. I just cited company randomly. There is no affiliation or anything. For cable tension measurement, landslide monitoring is a common application. So this is one of the IDS system for bridge monitoring. Sports, how do you measure the speed of a tennis ball? Well, it's a continuous wave radar, the same radar that's used for monitoring the speed of your car. One of my activities is subsurface monitoring. So if you not beam a radio frequency wave towards the air, but towards the ground, you can detect subsurface cavities or subsurface interfaces. This is commonly used in glaciology. This is the bottom of a glacier. And maybe you're reading the news on the BBC. Now, you're familiar with the BBC is very often using aerial images, spaceborne images from ISAR, which are visible images, but visible images you will not get when you have night or when you have cloud. And recently, there have been multiple commercial spaceborne radar, Umbra, Capella, which reach the same resolution as visible images. So now this is one of the BBC news from 2024, where you actually get the images with 25 centimeter resolution from spaceborne radar. If you're not into the commercial stuff, but you want some publicly available data, European Space Agency has launched the two Sentinel-1A and 1C. B is broken now. Maybe 10 days ago, the Indian Space Agency and NASA have launched ISAR, whose data should be freely available once commissioned. So you see that there's many radar around us, and including for civilian uses. So how can we develop our own radar systems? So we need a requirement. What are the requirements of the signals? The first one is radar systems require high power. Why is it? It's just energy conservation. You might be familiar, if you emit an electromagnetic wave, it spreads as a sphere around the emitter, and energy conservation says the density of power at a distance d from the emitter is emitted power divided by d squared. That's Fritz's equation. In the radar systems, this energy reaches a target, which is a point-like emitter itself, and this point-like emitter backscatters the energy towards you. So it means that you have 1 over d squared multiplied by 1 over d squared. We have a 1 over d fourth power, and this makes radar signals very weak. So first of all, we need high power signals for illuminating the scenes. Secondly, the second range, the range resolution of a radar, so you emit an electromagnetic wave, and an intuitive way of saying this, we emit a pulse, and the time resolution with which you can measure the time of flight is the duration of this pulse, which is also said the inverse of a bandwidth. So there is this range resolution equation which tells you the range resolution is the inverse of the bandwidth of a signal. You multiply by the speed of light to convert time into distance, and you divide by 2 because it's a two-way trip. Now, this is a core equation because it says the higher the bandwidth of a signal, the better the range resolution. But no one said you had to illuminate the scene with this bandwidth at any given time. The most naive approach, pulsed radar, says you make a narrow pulse, and this pulses, you measure the time of flight. Actually, it's very inefficient because you have energy compressed in a very short duration. Most of the time, you're not emitting energy. So you can also do a frequency sweep, frequency modulated continuous wave or frequency step continuous wave. So you can actually measure one after the other each frequency, and then I'll show you can inverse Fourier transform to get the resulting images. Or actually, what I believe to be the most practical application towards SDR is noise radar. So I will go through these 4 steps just to quickly show you that all of these are usable by the amateur developer. For the FMCW, I refer to Gregory Sharva. Maybe you remember that something like 10, 12 years ago, there was a big trend. This was an MIT lab session where they were developing this FMCW tin can, coffee can radar antenna at 2.4 gigahertz. And Gregory Sharva's book is amazing if you want to get introduction on short-range radar system. So very quickly, just to show you the challenges of each one of these methods, and especially to convince you that noise radar is most appropriate to software-defined radio applications. This is an example that we published about a pulse radar, and this is very much inspired by ground-penetrating radar. All ground-penetrating radar, to my knowledge, are based on this system, where you want to generate a narrow pulse, a sharp pulse, and this sharp pulse, well, it's not easy to tell a transistor or to tell a hardware, I want to squeeze as much energy in a sharp pulse as possible. And Jim Williams, the passed away analog designer from linear technology, wrote multiple books about the avalanche transistor, but the principle is that if you take a transistor and you polarize it at a high energy voltage, you will make a positive feedback loop. As it is heating up, it will let more and more power go through. So you trickle charge very slowly a capacitor, and then you tell the transistor, go empty the capacitor energy as fast as possible. And you can make sharp pulses. I don't know if you can read this. Is 2 nanoseconds, so 2 nanoseconds is inverse of 500 megahertz. So this is one trick for generating sharp pulses, and the second trick is when you want to record the pulses, well, you need at least twice the sampling rate of the shortest duration of your pulses. So you can take a radio frequency grade oscilloscope, which is not practical on the field. So if you take one of these STM32 microcontroller, which is fitted with a high resolution timer with 200 picosecond time resolution, you can make stroboscopy under the assumption that the environment is static during the measurement. You can repeat the pulses and measure at one time, then 200 picosecond later, 200 picosecond later, and you have an equivalent sampling rate of 5 gigasample per second, even though your microcontroller is only running at a few tens of megahertz. So if you're interested, you can make a very cheap, low-cost ground-penetrating radar using these techniques and addressing pulse radar. FMCW, frequency-modulated continuous wave, is a trick where instead of generating one pulse with as much bandwidth as you can, you say, let's sweep. So this bandwidth B that we had earlier here is now a frequency range delta F, and you can very well tune this frequency range from a start frequency to an end frequency. And you say you sweep this frequency range during a duration time T, and what you demonstrate if a reflector, a target, is located at range tau, then you duplicate this emitted signal at a time tau delayed. Now, if you mix the emitted signal with a received signal, you get a beat note, df, and if you wisely tune, so for example, delta f will be tens of megahertz, delta t will be a few microseconds, then the tau here, which is a few hundreds of nanoseconds, will end up with a df of a few tens of kilohertz. You can do the calculation here. And this happens to be in the audio frequency. So these are recordings I made using GNU Radio by recording on the sound card of my PC, of my laptop, the outgoing signal, which is actually in the few tens of kilohertz, and these are all the targets that you can detect in the Fourier domain after taking the beat note. So this is the core topic of Grigory Charjva's short-range radar system. Unfortunately, there's a little trick in here, is that when you want to implement this, well, the voltage-controlled oscillator usually do not have a linear frequency output with a driving incoming voltage, and the frequency offset at one point of your frequency sweep is not the same as on the end of your frequency sweep. This means that the frequency bit note at the end of a sweep is not the same as the one at the beginning, and you end up spreading your Fourier transform. So either you need to work on a narrow range of FMCW VCO, or you need to linearize your VCO. That's not completely trivial. Finally, if you have access to a vector network analyzer, well, a radar is no more than analyzing the reflection scattering coefficient S11, and you just take the inverse Fourier transform of the S11 because you swept each and every frequency one after the other. This is an example using a fancy microwave vector network analyzer I have access in the lab, and what you see is that if horn antenna is targeting a corner reflector, which is basically designed to reflect all the energy towards the emitter, you see that in red, in the absence of target, we have basically a flat line. Now, if I put a corner reflector in front of a radar, you have this sine wave, and actually this tells you how many nodes and antinodes you have between the emitting antenna and the corner reflector. So it's a standing wave pattern with as many nodes and antinodes as you have a large distance. You take the Fourier transform of this recording, and here you have your target. In blue, with a corner reflector, in red, without the corner reflector. So this little dot here is actually probably the tripod in front of a corner reflector. Now, not everyone has access to such fancy hardware, so you might want to reproduce this with the nano VNA. Now, the nano VNA lacks a bit isolation, so one thing that I love to do when I'm doing radar measurements, if you're familiar with acoustic devices, surface acoustic wave devices, convert electromagnetic wave in acoustic wave, which are much slower, and you can create reflections a few microseconds delayed with a device which is only a few millimeters in length. So this is an example of acoustic target measurement using a nano VNA. And just before coming, I tried to use a bit more fancy Libre VNA. The nano VNA, if you're familiar, is 30 euros. The Libre VNA is 600 euros. And this is set up on my balcony where I have the Libre VNA with Yagi-Uda antennas emitting the signal in the frequency domain. And by inverse Fourier transform, you will get some of the targets irrelevant of a number of points or irrelevant of a frequency range, but with some artifacts due to the fact that the antenna is not uniform over the frequency band. So what I'm trying to convince you here is that there's many ways that even amateur developers can address radar systems. But at the end of the day, what you're looking for is the resemblance of an emitted signal with a backscatter signal. What you want to measure is you're broadcasting a signal. This signal is backscattered by whatever reflector you have in the environment, and you want to detect this time of flight. Now, the quantity to detect the time of flight between a recorded signal and a known pattern that you broadcast is called the cross-correlation. Now, the cross-correlation is the pattern I transmitted, you sweep it by a time delay tau over the received signal, and only when the two pattern matches will the energy accumulate. Otherwise, you have mean value zero quantity and the energy doesn't accumulate. If your target is moving, then not only is your signal time delayed, but it's also frequency shifted. And one characterization of how good my signal is for radar applications is called the ambiguity function, where you take the autocorrelation, so the time delayed copy is my broadcast signal looking similar to itself as I delay it by tau. And furthermore, if I introduce some frequency offset, does it look similar to itself? We will see that this is important when we address passive radar, when we're not designing our own wave for radar application, but when we're using surrounding electromagnetic smog around us for radar applications. Now, correlation, you see that in the discrete form is n multiplication, with n the number of samples that you collected, that you must repeat for all possible delays another n value. So this is called complexity n-squared algorithm. This is computational intensive. So you don't want to calculate correlation this way. You actually want to use the benefit of the property of a correlation, which is closely linked to the convolution theorem, if you're familiar, that the Fourier transform of a correlation is the Fourier transform of a signal times the complex conjugate of the Fourier transform of a pattern. If you're familiar with the convolution theorem, convolution says the Fourier transform of a convolution is a product of the Fourier transform, and because this time we have the time in the opposite direction than in the convolution, now we need to take the complex conjugate to flip the time. The beauty of a Fourier analysis of a correlation is that now we have a fast Fourier transform, and the fast Fourier transform is an n log n complexity algorithm. So you gain a lot in terms of computational power. So what I like to do here is to demonstrate this concept using GNU Radio. GNU Radio is your free open source framework for software-defined radio demonstration. You can run it on synthetic data, but you can also run it on real data. And just to quickly show you how I demonstrate this concept using GNU Radio, I have a noise source. You don't know what kind of signal you're broadcasting, but you must remember what it is. So it can be any random source. This is called the reference channel. You must remember what you sent. And this is called the surveillance channel. The surveillance channel represents the target, the receiving antenna. And this receiving antenna will be exposed to a time-delayed copy of a broadcast signal. And this time delay, I will allow myself to set it manually using a slider. So I have a slider D here, and this slider, I will allow myself to change the time delay manually. You take the Fourier transform, multiply conjugate, inverse Fourier transform. The only trick is to calculate the Fourier transform. You need to convert the stream, the continuous data coming from the source, into a vector, because taking the integral requires that you have n samples to accumulate. And if you run this guy, and of course, no. Not this one. If you run this guy, is this going to work? Of course, you should never kill the terminal you launch GNU Radio from, otherwise it fails to run. So here it is. And that's the output. So you see here we're broadcasting a noise. The noise is detected with a 0 delay. And if I move a time delay here, you see your cross-correlation peak moving left and right as I'm introducing the delay. So what I'm doing here is I'm introducing a delay between the reference and the surveillance channel. And you see on the bottom of the Fourier transform on the inverse Fourier transform of a product, complex conjugate of a Fourier transform of a signal and Fourier transform of a surveillance, you see the position of a correlation peak. So this is a demonstration how you actually calculate a correlation in a software framework that does not know what a correlation is. If you search for correlation in GNU Radio, you will not find it. So this is my demonstration about how to calculate a correlation, but a beauty of a correlation is that since the Fourier transform is a linear operation, remember that linear means that f of ax plus by is af of x plus bf of y. And we just showed that correlation is a Fourier transform, and Fourier transform is linear. It means that if I get the backscatter signal of multiple targets, well, I will get multiple correlation peaks. How do I demonstrate this? Exactly the same story as before. I have a noise source. The noise source feeds the reference channel. And now I have 3 delays. These 3 delays are delayed, this time so that I don't change manually my delay, by a triangle wave, a square wave, or a sine wave. And these 3 delays are defining the delays of the 3 targets. Now notice that this here, this addition, represents the receiving antenna. So you have a reference channel, one receiving antenna, receiving the vector sum of all the targets that have been illuminating the scene, and then Fourier transform, multiply conjugate, each single inverse Fourier transform. We have 3 targets, but only 1 inverse Fourier transform. And when you run this guy here, what you will see is the 3 targets with 1 target delay shaped as a sine wave, 1 target delay shaped as a triangular wave, and 1 target shaped as a square wave. Okay? So you see that by understanding the correlation, the Fourier transform analysis for computing the correlation, and by understanding the linearity of the Fourier transform, you can actually implement your radar using GNU Radio, despite GNU Radio not being fitted with a correlation function. So what I'm trying also to show you here is that GNU Radio can be really a fun framework to get familiar with some of the mathematical concepts involved in software-defined radio radar. Now, having said this, I told you in the beginning we have pulse radar, FMCW, FSCW, and noise radar. And I believe noise radar is the most suitable approach to software-defined radio. Why is it? First of all, because noise radar is one of the earliest implementation. If you look at the references, they date from 1957, 1959, and noise radar is actually defined by we broadcast random signal whose copy we record locally, and then we try to find time-delayed copies. So how do you implement this with GNU Radio? Well, for example, you take a Pluto SDR, and the Pluto SDR is used for broadcasting a random signal. So here, I'm trying to take a random source, and this random source is feeding the Pluto SDR. So this is your emitter. And what you need is to remember what you broadcast. So you take a coupler, you take a fraction, a tiny fraction of the energy, and you feed it to the reference channel of a B210 SDR. And the second input of a B210 SDR is connected to the antenna. And these two guys here will be the inputs of a correlation. Now, what's important is that the B210 SDR is fitted with the analog device AD9361 front end, and this front end happens to be driving the two receivers with the same local oscillator. That's very important. We're going to see a bit later. So when you run this, you actually run the correlation between the two channels, and you see here, positive time, you have a slowly decaying signal. Negative time, well, signal doesn't propagate in the negative delay, so you have no signal. But you would be hard-pressed to detect a target because we miss range resolution. Your Pluto SDR can only broadcast 5 megahertz maximum. Your Pluto SDR can receive 8 megasamples per second, so you're limited to a poor range resolution. How can you improve your range resolution? Again, no one said you needed to illuminate the whole frequency range at the same time. So what you can do is frequency stacking. We just seen that that correlation is best computed in Fourier domain, so we're already taken the Fourier transform of a received signal. So what you can do is, before taking the inverse Fourier transform to go back to time domain, you stack frequencies that were collected, centered on 2, 4, 6, 8 megahertz, and once you've accumulated all the spectra, then you take the inverse Fourier transform, and this gives you the high range resolution to differentiate the various targets. And of course, I always plot the negative time, because if you see something in the negative time that you also see in the positive times, these are artifacts, these are not targets. So this is an example of using the software-defined radio radar on a ship. So this was done with my colleagues in University of Sendai with Wei Feng, where we went on the beach. So very nice, because you just need your two Yagi-Uda antenna. This was done using the RTL SDR DVB-T dongles and the laptop. Now, here you have moving ships, so that we have two information. You have, on the one hand, the velocity of the ships. Remember, 2 times the carrier frequency times the velocity divided by the speed of light, and the range. So to process this data, we need to run this rather computationally intensive, running all the correlation for all possible frequency offsets. If you want to repeat this at home, you have a GitHub repository with the data set and the script for running this. And what you will get, actually, are various targets. In the x-axis, you've got the velocity, the Doppler shift. In the y-axis, you've got the range, the biostatic range, the distance. And you got various dots here, which are the various targets. Now, if you do the quick calculation, if you say that a container ship is going at a few tens of kilometers per hour, you do the calculation, and you will see that the frequency shift is a few tens of hertz, which is indeed what we're seeing here, which might hint at why we need some more or less good oscillators. You can do the same with planes. This was done at airport of Sendai in Japan, here with a horn antenna and a Yagi-Uda antenna for checking how these can detect targets. There was another Yagi-Uda antenna facing in the other direction as a reference signal. This was all done with television broadcast signals. And in the case of planes, so this is not a trajectory in the sense x-y dimension, Cartesian space, but this is in the x direction, the velocity, in the y direction is the range of the plane. So if I make a quick movie of this, these are the ships. The ships are going in the negative Doppler shift, you will see these dots coming closer and closer, and in the positive Doppler shift, you will see these dots, which are various ships in the visible range of the radar, going away from the shore. So this is the shore, these are the ships, you see the range is a few kilometers, and you might have seen all this noise here. These are actually the waves. This is what makes maritime radar much more complicated, because you've got so much clutter with all the waves coming on the beach. So you've got a trick here, which is called direct signal interference removal. So we know that we don't want to detect the waves, we know we want to detect the ships, and I'll get into the quick details of what is DSI, direct signal interference removal. Again, if you want to reproduce this at home, you can download the data sets, there are a few gigabytes large, on iqengine.org. iqengine is a repository for software-defined radio data sets organized by Mark Lischman, and in the passive radar subdirectory, you will find all the data sets for reproducing this at home. So what is direct signal interference removal? You see here that on the short range, we said we want to cancel anything happening in a range shorter than the ships we want to detect. And this removes some of the clutter because we remove the short-range information here. So just to very quickly get into the DSI. DSI is about finding the time-delayed copies of a reference signal in the surveillance. So we have short-term copies, which we want to cancel. How do you find the weights of these reference signal in the surveillance signal? Well, these weights, you can say this as a matrix information. The surveillance is one bit vector, all the data you collected, and the reference matrix is actually all the time-delayed copies of the reference signal. So you see, I take the reference signal for R1 to Rn, so n can be very big, it can be 100,000 samples. And you say, I want to remove anything with 3 delays, 2 delays, 1 delay, no delay, that's your direct communication, -1, -2, 1, -3. And so this is a matrix with quite a few columns, maybe 10 columns, but many rows, maybe 100,000 rows. And you might know that the inverse of a rectangular matrix doesn't exist. You don't know how to calculate the inverse of a rectangular matrix. You know how to calculate the inverse of a square matrix. Now, Roger Penrose and others in the 1950s demonstrated that when you have a non-square matrix, you can calculate the inverse, and it's called the pseudo-inverse. It's using this formula, transpose of a matrix times the matrix inverse, because this is a square matrix, multiplied by transpose of a matrix, and this gives you a least square optimal estimate of the weights of the reference signal in the surveillance signal. Now, if you think this is all fancy math, I'm never going to use this, this is exactly what you're using when you do a fit of a function that you have many more samples than the number of parameters. So that's exactly what you're doing when you're doing polyfit under MATLAB. Finally, there is one last concept I need to introduce before showing you all the applications that we can do with radar, and it's called the pulse compression ratio. Pulse compression ratio is a fascinating topic if you're doing global navigation satellite system. It's the same reason you can detect GPS signal despite the received signal being 10 decibels below the terminal noise. Pulse compression ratio says I have a noisy signal. Now, if I want to remove noise, what do? I average. And if I average, I run a sliding average. If you just run a sliding average, good, you can remove the noise, but you also spread the information. You lose time information, but our radar system wants to have a sharp information localization. So what you want is to maximize the bandwidth. At the same time, you're maximizing the time over which you're running the average. And so the pulse compression ratio is the product of the bandwidth of a signal we're broadcasting multiplied by the duration of this signal that you're broadcasting. Now, the PCR in the analog time was an analog quantity, but if you think nowadays of a digital domain, well, the bandwidth is the number of bits per second that you're broadcasting, and the duration is the bit rate multiplied by the number of bits. So actually what you show is that when you're generating a digital pseudo-random sequence, the pulse compression ratio is given by n, the number of chips that you're broadcasting. So the longer the code, the better your pulse compression ratio. And what does it mean quantitatively? It means that if I hide a signal, and actually you can run this if you want to copy these lines by yourself in Octave, you will get the same result. This is two known copies of a signal in a noisy signal, you would be hard-pressed to detect where this broadcast code is. But by running the correlation, this is 2048 chip long code, you see that you gain about 20 dB gain on the signal-to-noise ratio, and you can extract the signals whose width here is determined by the bandwidth, the chip rate of what you're broadcasting. So it's a very important concept because it allows you to raise the signal above thermal noise, or noise in general, and actually it means that if you're doing noise radar, you can emit below the noise, and no one will know you're emitting because you're under the noise. So I know people are doing this with geostationary satellite as well. As long as you're broadcasting below the noise, no one will detect you, and you're the only one who know what is the pattern that you're broadcasting, so you are the only one who can detect these backscattered signals. So having said this, let's try this with one of these little receivers, which is called the Pocket SDR. So the Pocket SDR was developed by a Japanese researcher, Tomoji Takasu. Initially, the Pocket SDR is dedicated to global navigation satellite signals. The beauty of this is it's a 2-bit A to D converter, because when you're working with low signal-to-noise ratio, the only thing you're quantizing with high-resolution A to D converter is noise. So you don't need to quantize noise. You just want to quantize information in the time. And this is what the 2-bit A to D converter is doing. So Tomoji Takasu tells us, use a MAX 2771, which has up to 40 megasample per second, sampled on only 2 bits, but doesn't matter because most of our information is below noise. And actually what we do is we put 2 of them so that we have one reference channel, one surveillance channel. The only trick here is that this is dedicated to L-band, 1 to 2 gigahertz. Most of the signals of interest are sub-gigahertz, so you need an external frequency transposition frequency circuit, a mixer, to transpose the incoming signal to the L-band. So if you run this, you see here, this is a television broadcast channel in the area I live in Besançon in France. So what I'm doing here is passive radar. I'm using the signal broadcast by television emitter, and I'm looking at a direct Yagi-Uda antenna facing the emitter, and another Yagi-Uda antenna facing the seed I want to detect. And you see that on all these frequency channels, which are all television channels in the French system, you have, in the negative time, no target, hopefully. And in the positive time, you see that we have always, I put a red line here, at the equivalent of 240 meters, if you convert by the speed of light, which is a two-way trip of 137 meters. Now, I told you here I have an emitter at one location, the receiver on my balcony, and how do I know where the target is located? And in a bistatic radar, the emitter is located over here, my balcony is located over here, and you can draw an ellipse. You can demonstrate that the site of all the reflectors are an ellipse, and this ellipse holds all the different time delay between the direct signal and the signal bouncing on any target over here. And I assume maybe one target is a large building located from my apartment about 500 meters away. But the bistatic range is 137 meters. Why do I say this? Because when I look from my balcony, I have here a big reflector. So you see that interpreting the time domain delays into a spatial domain information is not so obvious. And this brings us to spatial diversity. Maybe we don't want only range information, but we also want to have azimuth information. And there's no mystery. If you only have one emitter, one receiver, you only get one information where the target is located on a circle centered on your emitter receiver. But now if you have spatial diversity, you want to move the antenna and point in different directions. Historically, you would do this with a big antenna, because the bigger the antenna, the narrower the beam. It's just given by the beam width is wavelength over the diameter of the antenna. Now, if you look at modern antennas, you go away from these big dishes, very expensive, prone to mechanical failure, for electronic steering. This is SCAT toward SCAT 3D. This is marine radar, where the marine radar has to track the satellite, even though the ship is moving left and right. And by steering, by changing the phase between the emitting elements, you can steer the signal. So you see that if you have a uniform linear antenna array. And these antennas are separated by a distance d. Then by introducing a phase delay between these various elements, you can steer the antenna in a direction theta. And this theta here is only determined by the phase offset, where you create constructive interference in one direction and destructive interference in all other directions. If you want a detailed explanation, Hendrik Forst's website is amazing about synthetic aperture radar. Now, one way of doing this is to say, I will copy multiple copies of the emitting antenna, and I will have multiple antennas. This is called multiple input, single output, or multiple input, multiple output. This is what your Wi-Fi router is doing when you've got 2 or 4 antennas. But this is very complicated because each one of these antennas is introducing its own delay. You need calibration of a delay. So what I prefer is to take one antenna and to move it in different locations. So this is called synthetic aperture radar. So during COVID, well, you had infinite amount of time, nothing to do during the day. So I was on my balcony with my antenna doing radar, trying to range the building opposite of my balcony, and I wanted to have azimuth resolution. So what I did is, on my balcony, I drew the graduation, and I just moved manually the antenna to each and every new position. And I collected the spectrum for each one of these positions, and that allows me to have azimuth resolution. How is it? Because if you remember, we said these signals have a constant phase. What is a signal where you introduce a constant phase between the various elements? Well, actually, you can demonstrate that the phase offset is 2 pi, the antenna step, divided by the wavelength multiplied by sine of theta. And if you have dots with regularly oriented phase, this is called a Fourier domain, Fourier transform, because you have regular phase pattern. So actually what you do is you collect in the time domain for each position many samples, you move them along the azimuth position, and then you take a 2D Fourier domain. We saw that correlation is a Fourier transform along the time domain, and now azimuth compression is a Fourier transform along the antenna positions. Of course, many fewer antenna positions than time domain. So you run this, I will not get the details on the GNU Radio script that you run, where you collect the data, you stream the data. I find it easier to separate data collection, data processing, so I use 0MQ, publish, subscribe. And this is the example of what you get. So here's an example of azimuth range. So you've got range, you've got azimuth, and you see that I can put various targets, and these targets will match some of the buildings opposite to my balcony. And the beauty of this, if you feed this to QGIS, there is no degree of freedom. The only degree of freedom is the orientation, but the range is only determined by the bandwidth, and the azimuth is only determined by the step of your antenna motion. So this is synthetic aperture radar, taking measurements for various locations and inverse Fourier transform along the azimuth position. Later, I got a bit more money. I bought myself a nice rail. Now this is all automated. You can move the antenna automatically, and that will give you the synthetic aperture radar measurement. So when you do SAR measurements, and again, you can go through this by yourself if you want. So the first thing is you take all the range information along the various antenna positions. Then you take the Fourier transform along the time domain, which gives you, remember, Fourier transform of a pattern multiplied by Fourier transform of a measurement signal, complex conjugate, and inverse Fourier transform. This gives you the range compression, and then you take a Fourier transform along the azimuth. This gives you azimuth compression, and then you convert azimuth range into angle range, and this is what we're feeding QGIS. So if you go through this, it's actually 20 lines of MATLAB processing. And that's an example here. So you see that my new rail here that I'm using is illuminating our university building. And these are, for example, the circular targets of this room here. You've got the portal at the end over here. And if you look in this direction, you've got the various buildings and hotels facing in your direction. So again, this is all working quite well. You've got the GitHub with a demonstration of how to develop if you want to reproduce this at home. And power total consumption is about 20 watts, so you can run this on battery. So actually, I told you can use opportunistic sources of signals. I introduced in the beginning that there's more and more Spaceborne satellites. The fun thing is actually you can use Spaceborne satellite illumination for ground-based passive radar. This is an example using Sentinel-1. The European Space Agency tells you what is the frequency and what is the time when the satellite will fly over your head. So you can actually record using one antenna the signal beamed from the satellite. With a second antenna, you look at the surrounding environment. And if you do the same processing I just told you, you can get over a digital elevation model the various reflections, and you see that they match nicely the various topographical feature of the surrounding area. So now we have more and more satellites in more and more bands. So actually this is becoming more and more ubiquitous processing that you can try by yourself. Yeah, that's the nice thing about this is you don't need to know a detailed properties of orbit of a satellite. All you need to know is the distance, meaning the speed at which the satellite is flying. The only thing you need is the speed, which tells you how often the satellite moves between two measurements, and that's enough to reproduce, again, no degree of freedom in azimuth or elevation, azimuth range mapping. And finally, the last thing you can do, we've been discussing so far only about magnitude, but a radio frequency quantity is a vector information. It's got a magnitude and a phase. So if rather than just using the magnitude, you actually look at the phase of each one of these targets, you can get a range resolution much lower than the inverse of the bandwidth, and that's given by the interferometric measurement, the phase difference. And the phase difference has an ambiguity of 2 pi, which is the two-way trip of a wave, but this is actually what is used for landslide monitoring, where you're actually looking at the phase of information. I will not get in the details because I'm running out of time. I just, for the sake of introducing the last topic, is inverse SAR, ISAR. When you're doing synthetic aperture radar, you're moving the antenna, but maybe you don't have the opportunity of moving the antenna. It's the target which is moving. And to give you an example, this is a continuous wave radar located 40 kilometers from our laboratory. And this continuous wave radar is a Spaceborne, a space surveillance radar, the French GRAV, space surveillance radar. And whenever a plane is flying through the beam of this continuous wave radar, it generates a Doppler shifted signal. So this is very easy to record from the laboratory located 40 kilometers from this emitter. Now, if you take one of these signals here, and during daytime it's very crowded, but during nighttime you have much fewer planes, and then you can isolate one of these planes. And what happens is, as this plane is flying inside the beam, you've got the faraway wing, which is farther away than the nearby wing, or you've got the tail, which is at a different location than the nose, and they will introduce different Doppler shift. So ISAR is about micro-Doppler analysis. Once you've removed the coarse shape of a motion of a path of a plane or of a ship, because this is often used in maritime radar, you will end up with a sub-Doppler analysis, and this gives you a signature of what this target might be. Now, the challenge here is these micro-Doppler. You see that they are very tiny. If you simulate this for a commercial plane, a 40-meter wide plane, it will be only a few fraction of a hertz. So you need measurement over tens of seconds to be able to resolve this kind of Doppler shift. So this brings me to my conclusion, where I wanted to introduce to you the various means of generating a bandwidth for ranging and detection of electromagnetic wave. We're doing this using low-cost software-defined radio, RTL SDR, B210, Pluto SDR. If you have a radio frequency grade oscilloscope, you can do radar using oscilloscope. There's many more applications of this beamforming, synthetic aperture radar, whether you're doing global navigation, satellites, signal processing, spoofing, anti-spoofing. You can do radio astronomy. It's an opportunity to get familiar with so many topics related to GNU Radio and radio signal processing, including passive radar, which makes it legal for you not to broadcast any signal. If you want more information, you can look at the videos online of the GNU Radio conference held every September in the US, the FOSDEM Software-Defined Radio Dev Room, the Software-Defined Radio Academy in Friedrichshafen in July, and our European GNU Radio Days. And if you want a detailed analysis, we released with my co-author, Hervé Beuglen, beginning of this year, a textbook where 2 chapters are devoted to radar processing. And with this conclusion, I thank you for your attention.